Okay, so I would like to finish the discussion of anomalies in hydrodynamics today, and I will start after that. I will try to tell you how the an approach, some modern approach called holography can tell us, can at least establish some connection between gravity and hydrodynamics. So last time we have started discussing the hydrodynamics of superfluid with chiral anomaly. So what we imagine is the following: we have some material or some system which have Dirac point that are Dirac fermions, massless Dirac fermions, left-handed Dirac fermions and right-handed Dirac fermions. Let's imagine that there is some density of both. Each of these, they might be different. And then some process, for example, Cooper pairing would make the fermion pair with each other and they form a superfluid. And let's assume that for simplicity, we have only the right-handed fermion. They pair form superfluid. It's assumption that usually make the hydrodynamic description much simpler, because we know that for superfluid, we have T equal to 0 superfluid. We have Lagrangian description, action based on the action principle. In the absence of anomaly, the system is described by an action, which is integral over d4x, p, that's the same function that give us the dependence of pressure over the chemical potential. And then here, instead of the chemical potential, we have a covariant, a relativistically covariant combination of derivatives. So let me write this, me minus h d mu phi d mu phi. Phi is the phase of the phi is the phase of the condensate, and in the equilibrium state, this phase rotates linearly in time, and if we are away from equilibrium, there will be a fluctuation phi tilde. So that action gives us the description of a superfluid. Let me also tell you that mention that this in the non-relativistic limit reduces to the usual to the Lagrangian that would give rise to the usual hydrodynamic equation of non-relativistic fluid. So here we have the Galilean combination of time derivative and spatial derivative of the this phase phi. Basically, here you just assume that this phi tilde is very small compared to mu t, expand, and then you get this term. So here the derivative here, when I write this derivative, I have also taken into account a possible coupling of this Goldstone boson with external electromagnetic field. So this Lagrangian description leads to the equations, for example, the equations of conservation of particle number. Is just an equation of motion following from this action. So, for example, maybe let's do that here. If I have my Lagrangian being pressure is function of minus d mu phi squared, right? We know that the Lagrangian equation of motion is derivative of the Lagrangian with respect to the derivative of mu times d mu, right? Minus dl over d phi equal to 0, standard field equations of a field theory of one single scalar field, phi. Now, this pressure does not depend on phi alone, because there is a reason for that. The phi is a phase, so the Lagrange, all physical quantity only depends on the gradient of the phase, because the absolute point, the absolute value of the phase is arbitrary. So this is 0, and this one derivative. Now, derivative of pressure over its argument, dp over d mu is n. Right? And so this term gives us d mu of n time derivative of the square root. So when you do this, you find that d mu phi divided by square root of d mu phi square is equal to 0. Right? So that is the equation, d mu and u mu is equal to 0. It's the conservation of particle number. The other equations, the equation of conservation of energy momentum tensor, is it actually follows from this equation, and the fact that the velocity basically is a gradient of the phase. The velocity is the gradient of the phase divided by the square root to make this velocity have unit norm. D mu, this can be shown to follow from that equations. But there is another way, more symmetry-based way to derive the equations of conservation of energy momentum tensor, and that requires us to at least to derive these equations in an easier, less computational intensive way, at least convince ourselves that this equation is valid, is to mentally put our system in a curved space-time. That is the technical device very commonly used in field theory to derive relationships that involve the stress energy tensor, because the stress energy tensor is, in a relativistic field theory, can be defined as the derivative of the action with respect to the metric g mu nu. So if I have some action which is a function, say, of my phi, functional of my phi, and some g mu nu, which is some external metric, I can normally, when we are dealing with some superfluid in the lab, we cannot put the system in easily in a curved background, but in principle it can be done. In principle, we can imagine that just next to us there was suddenly supernova explode and g mu nu would become non-zero. The systems would know how to couple to that G mu nu, metric, right? And then if I take the variation of that when I change the G mu nu, I can define my stress energy tensor. So basically T mu nu time variation G mu nu. There's a square root of minus G in front. So here, where is this dependence on the metric come from? If I write the action in a curved background, I get, first of all, the volume of space has to come with the determinant of the metric. That's the volume of region of space-time is the determinant of the metric. And then here inside the argument, I also have to put the real metric of space, G mu nu, instead of D mu phi, D mu phi. And when you do this variation, there is two places where G can change, here and here. And take derivative the variation of S with respect to G. We see two terms. One term is that G mu nu times P. And then from this term, we get this epsilon. You can convince yourself that it's what's coming from here is N, basically N times mu mu, which is epsilon plus P u mu. And U is this. And the it's just last time we have said how to include the anomalies. So if we have anomalies, like if our fermions that form these Cooper pairs are chiral, then the anomalies can be summarized as another term in the Lagrangian. So Lagrangian is P square root of minus this d mu phi square. And then plus, now I'm going to write it with some coefficient that required some calculation to fix. Just some, I'm just not going to fix it here. And then a term that has a very characteristic form of a coupling of an axion with the electromagnetic field. So basically here, this Goldstone boson, let me call that phi, coupled through a vertex that has in terms of the Feynman diagram, it looks like this Goldstone boson is coupled to two photons, one is A, the other is F lambda rho. So this C turned out to be related, can be fixed from the condition of anomalies, that d mu J mu is equal 1 over 4 pi squared E dot B, as we have derived in one of the previous lecture. You can see this emerging from the equation of motion as well. Let me do it in a simple way, actually glossing over some subtleties that I don't have to always have to deal with when we talk about the anomalies. But roughly speaking, the equation of motion that I have written before, right, now has an additional term So the first, when I take derivative with respect to d mu, this pressure gives me the usual d mu of n and u mu. That is the, you can see from here that current. And then from here you have derivative of this AF. So epsilon mu mu lambda rho d mu phi A mu A mu F lambda rho. And this is nothing but E dot B. Derivative, this is like epsilon mu mu lambda rho dA d mu A mu d lambda A rho, which is E dot B. So the anomalies in hydrodynamics of a superfluid can be quite compactly taken into account in the Lagrangian formalism by adding axion coupling of the Goldstone boson with electromagnetic field. Any questions? That everything that is basically where we stopped last time.
I had just a very minor question on the previous slide. In the final equation where it's P of square root of G mu nu, here the covariant derivative was used, and that's the covariant derivative including like the Christoffel symbol, right?
We don't
or
have
is
to,
that
you mean here? Or
yeah,
the derivative? Yeah, derivative here doesn't require Christoffel symbol because it's only when you write derivative of a vector, you need the Christoffel symbol.
oh,
Derivative
of,
of a scalar is just a derivative. Yeah.
Yep.
So
okay, great, thanks.
Yeah, when we write, for example, equation of motion like this one in curved space, then that requires us to put in appropriate Christoffel symbol, etc. Okay. But here we don't. Yeah.
So if you weren't including the electromagnetic field, you could have just written a partial derivative in that specific place.
Yeah, if I don't have electromagnetic field, that would be partial derivative.
Thanks.
So this one doesn't have, is just like in flat space. D mu phi is still d mu phi minus a mu. No, it's nothing different from the flat space.
Thanks.
Mm-hmm. Now the anomalous, the hydrodynamics of a non-superfluid, of a normal fluid with anomalies. It's a complicated, it takes some time to derive using the standard methods with writing down all the equations, making sure that the entropy is, the production of entropy is positive. But in one limit, the answer is simple. So that limit is somewhat restricted limit. That is a limit when the temperature is small. So in the relativistic system, we consider temperature much smaller than the chemical potential. So in this Dirac fermion, have some chemical potential, mu here. At zero temperature, all the states below that are filled. When the temperature is non-zero, we would smear out this Fermi surface become fuzzy, but the range of fuzziness of this Fermi surface, the typical excitation around the Fermi surface have temperature T. Right? So we imagine a slightly fuzzy system with slightly fuzzy Fermi surface. Okay, so this is the limit where now I'm retelling you the content of the paper by Abanov and Monteiro. So in this limit, let's assume temperature is zero, though. Zero temperature, we cannot make temperature completely zero without going away from the hydrodynamics behavior. To have hydrodynamics, you need particles to collide with each other, and that requires some finite temperature. But let's assume that the temperature is still very small compared to the chemical potential, and we are in the regime where hydrodynamics works. Okay, in this case, the usual hydrodynamics, normal usual hydrodynamics, we have T mu nu equal epsilon plus P G mu nu, oh, sorry, U mu U mu. By the way, is P plus P G mu nu. Okay, and we know from thermodynamics this epsilon plus P is equal to, we have used that many times, Ts plus mu n. At low temperature, this Ts is zero. So we just ignore this Ts. Ts is equal to zero. Set that to zero. And then we have here only mu n. And then in this limit we are trying to work with, the energy is only a function of n. There's no temperature. Pressure is a function of only n or chemical potential. There's no ignoring the dependence of everything on temperature. So this hydrodynamics is, if we know this equation of state, the hydrodynamics is at least mathematically consistent. It's a consistent theory that we can write down, because there's no entropy production. That is, we have this equation, d mu T mu nu equal to 0. And then the mu J mu is equal to 0. In this case, we have like 4 equations here and 1 equation here, total of 5 equations. This 5 equation is written for 4 variables because temperature have followed out from the set of hydrodynamic variables. Mu, chemical potential, that's x, and the velocity, which count as 3 different components of the velocity. This u square has to be -1. So 1 equation is extra. And that's basically, you can check that these 5 equations are not independent. There is one relationship between these equations that come from u mu, T mu nu equals to 0. That equation is equivalent to d mu, J mu equal to 0. You can check. And so this is the theory that we have written down is still a consistent theory with no contradiction. So within this regime of low temperature, that is the regime where Abanov and Monteiro work. So the first thing that they notice, so let me go step by step, is that there exists relativistic version of the Clebsch parameterization. So let's recall what was the Clebsch parameterization in the non-relativistic hydrodynamics. So in the non-relativistic case, a superfluid would have the velocity equal to some constant, which h bar over 2m, gradient of a phase, h bar over m. So that cannot be, it's this condition that the velocity is gradient of the phase, or would lead to irrotational flow, and that condition cannot be satisfied for an arbitrary solution, arbitrary configuration of the velocity in non-relativistic normal fluid. So in normal fluid, in the in non-relativistic hydrodynamics, one parameterization that is very useful is to write the velocity as gradient of some theta plus alpha gradient of beta, and treat three components of V with three functions, theta, alpha, and beta. And we have seen that various interesting things can be done using this formalism. For example, this the density and theta form canonically conjugate pairs. The Poisson brackets of n and theta is 1, and also I think n alpha and beta also form a canonically conjugate pair of variables. So going from superfluid to non-superfluid amounts to introducing two more so-called Clebsch parameter, alpha and beta. So in the relativistic case, so now one can write the following: U mu is equal to, now let me write it, some vector xi divided by its square. So that u square would be still, u is still a unit vector, but that xi, now I write as mu of theta plus alpha d mu beta. Just very obvious parameterization of three components of u. So u is a unit vector, so it has three independent degrees of freedom. Vector u, and then the zero component of u is completely fixed by the vector, by the spatial component. And now here we just chosen to parameterize these three components using three functions, alpha, beta, and theta. And now one thing one can also show is that the normal fluid mechanics equation of non-relativistic hydrodynamics relativistic hydrodynamics can be written as an action principle. So the action principle is very simple. V4x in pressure. Now, pressure as a function previously is the function of square root of d mu phi square. Now square root, just square root of minus mu. Yeah. So one can check that by brute force, one can check that the action, the variation of the action with respect to theta, respect to alpha, with respect to beta equal to 0 is equivalent to the hydrodynamic equations. That requires some work, but one can also use a slightly more clever way. Just, for example, we can couple the system to electromagnetic field and use gauge invariance to find the conservation for the conservation of charge. So the way to do that, let me show you this way to do that. We take this C mu equal d mu phi plus alpha u mu beta. In the case when we have the electromagnetic field, clearly we have to replace this C by C mu minus A mu. Just like in the superfluid case, we replace d mu phi with d mu phi minus A mu. Basically here, phi can still be thought of as something that would become a phase of the condensate if the system becomes superfluid. The system becoming superfluid basically means that this alpha and beta falls off from the Lagrangian. And so the Lagrangian in of normal fluid, relativistic fluid, in external field can be written as square root of minus g. Now I'm including even the external gravitational field minus g mu nu, c mu minus a mu, c mu minus a mu. And the conservation law are just consequences of the symmetry of the action with respect to gauge transformations and to diffeomorphism, that is coordinate transformation. So the conservation law, for example, d mu j mu is guaranteed if this j mu is the current obtained by variation of the action with respect to the gauge field a mu. And when you compute this, you find this derivative of pressure with respect to the S argument contains A here. And one can check that this is just N, because You have to take derivative of P with respect to chemical potential n times u mu, where u mu is C minus A mu square root of minus C minus A square. And the same for conservation of stress energy. If the stress energy is the derivative of the action with respect to the metric G mu nu, then we get the we get automatically, you can see this equation follows automatically from the equation of motion. But computing this, computing the stress tensor this way, we can see directly how the hydrodynamic expression of epsilon p u mu u nu plus p g mu nu jumped out from this action. It jumped out from this action in exactly the same way as it did in the case of superfluid. The introduction of this alpha and beta Krebs parameter changes the physics in a doesn't change the equations at all. All it does to the formalism is that it enlarges the class of velocity configuration that can be described by this hydrodynamic theory. So that is a fluid without any anomalies. And the new thing that was done by Abanov and Monteiro is to figure out how to modify this formalism to get the to put in the anomalies in hydrodynamics. So to put in anomalies, we do something very similar to the case of superfluid. We add a like axion-like coupling of the hydrodynamic degrees of freedom with the external field. So the first term is still like before. Now we add another term. Let me again write this with the undetermined constant C. That would require some work to fix, but then qualitatively we can write the what we expect like this: A mu C mu G lambda and here I would like to write the following: A rho plus C rho. Okay, so there are two modifications to the superfluid coupling. First of all, instead of the derivative of that Goldstone boson field that was staying in, instead of C before this position, I include the full velocity, well, unnormalized, this unnormalized velocity of my fluid. And also we add this is a new term. But it's new because if we did that in the case of a superfluid, it would guarantee to give us 0. Remember that derivative, we have epsilon tensor derivative here. And then if this one is another derivative, d rho of phi, that anti-symmetrization would give us 0. So in the case of superfluid, we don't have to worry about this term. So So what is the argument that lead Abanov and Monteiro to this form of the anomaly terms? So the requirement that fixes this term is that under gauge transformation, the gauge transformation makes a mu go to a mu plus d mu sub lambda. Phi goes to phi plus lambda. And alpha and beta doesn't change at all. Phi is what exactly like phase of the condensate, and then let me write here C mu equal d mu phi plus alpha d mu beta. Under these gauge transformations, the requirement is that the action sorry, this has to be minus. If I write this way, I need to include here something to make this gauge invariant. Sorry. Second square root of psi minus a square. Because psi minus a is invariant. So the requirement that that one impose on a quantum field theory to make it consistent with anomalies is that the change of the action in a when we make a gauge transformation has to be equal to the integral of the gauge, the parameter of the gauge transformation is lambda times ff2. So this time epsilon mu lambda rho d mu a lambda d, let me write in a better way, f mu f lambda rho with a coefficient, some coefficient that is fixed, completely fixed by the anomalies. In other words, anomalies is a breaking of conservation of current due to the gauge field, but that breaking is not arbitrary. It's completely prescribed, and so the non-invariance of the action with respect to the gauge transformation is also prescribed. So from that, one can see how this structure appears. So let's check that this structure is the structure that gives rise to an action that is invariant, is non-invariant. This term is non-invariant with respect to gauge transformation in the correct way. Okay, so there's various things that we can do. So all the terms here transform under gauge transformation. So let me look at this. Epsilon mu lambda rho a mu c lambda d mu a rho plus c rho. Okay, so from a here I get the term which is epsilon mu lambda rho d mu lambda xc nu d lambda a rho plus c rho. And when I write this term under the integral, I can do integration by part, and I can push this derivative to act either here or to act here. But when you act next to d lambda, because of the epsilon tensor, I get 0. So this term becomes minus epsilon mu nu lambda rho d mu c nu d lambda a rho plus c rho. This term already illustrate for you this. It's not guaranteed that when you write down something like this, you get the correct answer. For example, here we get a term that in the transformation that is not of the correct form, like epsilon mu nu lambda rho d nu d lambda a rho. So now the other one is d zeta d zeta can be shown to be 0 because of that this form of the xc. If c mu is equal d phi plus alpha d beta, you can convince yourself that epsilon mu nu lambda rho d mu c nu d lambda c rho is equal to 0. That's quite easy to check. Basically, because if I take the curve of this c, the curve of this c is all from alpha and beta. This d mu c nu minus d mu c mu is alpha, basically d alpha d beta. And when I take one of these d alpha and beta and multiply to the other d alpha and beta, with all the indices anti-symmetrized, I get 0. And so this is a term that that appears that doesn't have the correct form. The one that has the correct form is the one that comes from variation with respect to this xc and variation with respect to this xc. Give us something that has the correct form of epsilon a d c d lambda dA. And after integration by part, we get dA with an epsilon tensor that has the correct form. And the sign here that was chosen correct to cancel out to have the contribution. So the contribution that have to cancel is the two that come from variation with respect to this A here and A here. At the end, after doing all this calculation, one can check that this is the only possible structure that would be consistent with the condition of anomalies. With this condition fixed by requiring that the field theory reproduces the anomalies. Some simple but rather formal calculations, but it leads to interesting physical consequences. Let's look at some physical consequence of this neutron. So here, what we can do is to compute the current out of this, the charge current, J mu equal ds over dA mu, and there is just usual terms from the pressure, but from the new anomaly terms, you can imagine mentally just getting rid of this A, and the rest will be the current. And the rest, that one would be the current. So the current contains something like this: epsilon mu lambda rho psi mu, and then I'm going to just write the relative coefficients, the absolute coefficients, etc., is going to be dropped here in all these equations. There's some, maybe some coefficient here, some relative coefficient between these two terms that in principle can be fixed. So here we see the following effect. First effect is the effect that we have argued for before, the so-called chiral magnetic effect. The chiral magnetic effect comes from putting the system in, so let's see mu is the basically the velocity. So if the fluid is at rest, this is basically 1, 0. It's mu with the upper, to be pedantic. And then this J, vector J here, you can see this index is 0, this index is 0. And then mu, lambda, and rho are vector index. And so we have here derivative of A that is basically equal to, has to be mu times B. It has to be mu. Actually, this is not, what I'm saying here is not entirely correct. This is U mu. U mu is equal to 1 and 0. But that U mu, C mu, is derivative of phi plus alpha derivative of beta. And we know phi is equal minus, have to be minus mu t in thermal equilibrium. This mu is basically, it's like a chemical potential, but a vector, a relativistic version of a chemical potential that is like a vector in 4 dimension. C is mu times U mu. And so this one with mu equal to 0 give rise to the coefficient mu, and this is B. And the coefficient in front is related to the anomalies. Some coefficient here. So that has been talked about. We talked about even that this can be understood physically by looking at the spectrum of the fermion in a magnetic field. There is Landau level, and there is one single Landau level with just one chirality, and we fill up all the states, and there are states that move in one direction, and that gives rise to that current. So the current coming out from a fermion with a given chirality in a magnetic field is non-zero. It's when you put fermion with a given chirality in a magnetic field, it tends to move along one direction. And there is a second effect, sometimes called the chiral vortical effect. That come out from epsilon mu nu lambda rho c mu d lambda c rho. Contribution to the current of this form would have to include in it the following term. So here nu can be set to be 0. and that give us chemical potential. So this one is, we know that once this is 0, all the other have to be spatial components. So it's like mu epsilon I j k, right? If mu is I, d j c, c is mu again, mu uk. So it's proportional to mu square times curl of v u. So u of k is v of k. So let me write curl of v. So there is contribution to a current of the chiral, the number, basically the number of chiral fermions in a rotating fluid. So in the constitutive relations, there would be a contribution that tells us that if we take a fluid and then rotate it, the currents start to move in the direction of motion of this fluid. This term also arises from a more traditional treatment of looking at the entropy and make sure that entropy production is positive. But it is quite striking because if I'm thinking about a non-relativistic version of that phenomenon, there seems to be no analogy. So if I just take some system, a container of a non-relativistic fluid, and then I can imagine mimicking the chiral fermion by putting into this fluid particle with chirality. So for example, I can imagine taking a cup of water and put sugar into it. Sugar has 2 different chirality, but the one that we eat has 1 chirality. It's like a single. The sugar is like neutrinos in this way. And then we try, if we take this fluid and then we imagine a cup of this fluid, and then if we rotate it, then we can set up a flow with non-zero vorticity. Now these sugar molecules that we have in here, we can ask whether they would move along the direction of motion of the fluid. That is, if we have 2 different types of sugar, we can ask whether the 2 different chirality would separate themselves from each another. So now if you have this process conceivably can lead to separation. If imagine that you have a particle with a shape of a screw. If I rotate that particle with respect to water, then this will propel itself. If a particle is chiral, it can propel if it rotates with respect to water. The problem here is that when we rotate this water, the molecule themselves at some point will rotate with the same angular velocity as water. And so when that is reached, this condition, then there is no propeller effect anymore. This particle will sit in one place. There is no difference in the motion of the left-handed or the right-handed sugar molecules in the non-relativistic fluid setup like this. But in the apparently in relativistic system or system with the important thing is that this system has to have anomalies. There is an effect which has been seen using various methods, not just these action method or the entropy method. All methods indicate that in theory with gravity, theory with anomalies, there is in the constitutive relations is nu mu, and then we have another one term that looks like epsilon mu nu lambda rho. U nu d lambda u rho. And the coefficient in front is mu squared plus some another constant time t squared. And both are fixed by different type of anomalies. In the theory of Abanov and Monteiro, t put to 0. So they see only the t squared, a mu square part. Any question that I can answer? Okay, so let me briefly tell you about something that may have been seen in experiments.
Sorry, Sam, can you clarify on the previous you explained it, but I missed it. Why, when it's non-relativistic, like why is it needed that it's relativistic for this chiral vortical effect
to occur?
Yeah.
Yeah, I only have this this picture that I'm drawing here. That if I have just chiral particles without anomalies, then rotating a fluid by itself will not lead to the motion of this particle, because under rigid motion, particle will not move if they rotate with the same velocity with the fluid. More formally, I can do the following. I can try to modify the I can take the for example, take the non-relativistic hydrodynamic equations, and then ask if there is a modification in which J, instead of just usual term, I add to that something that proportional to the curve of V. Then in the entropy production, I get a new things, mu over something like mu over T, gradient of mu over T times curve of V. And at this point, I think I couldn't find any way to make this go away. Maybe
you mean you can't find
a good
why do you want to make it go away?
So I want to have some, maybe I didn't do it carefully enough, but I want to modify the equations of hydrodynamics so that the entropies, despite the fact that there is new term like this in the constitutive relation, the entropy would still be increasing. Yes, at least I want this term definitely would have to be non-dissipative to be consistent.
Because essentially you want still to be an equilibrium effect. That's why you want the entropy to increase.
I want the entropy has to increase independent of the initial condition. So if I start my solution from some initial condition, I want the entropy to always increase, and that seems to be not an easy thing to do with the usual hydrodynamic equation. The structure of this equation is quite restrictive. In three dimension, there is no. I haven't found a system modification. In two dimension, you know that there is this whole viscosity or odd viscosity. But in 3 dimension, it doesn't seem to be consistent. The way that the relativistic theory goes around this is that not only we modify this constitutive relation, the equation of motion themselves are modified. That is the conservation law for the current is not d mu, j mu is not 0 anymore, but equal ff dual. And so that completely fixes necessary modification in, say, the current, and current is equal to p. Now, at the very naive level, actually one can sort of understand that a rotation must have the same effect as the magnetic field. At the end, if I have a rotating system, a particle, when particle move in a rotating frame, there is Coriolis force that acting on it, and that is similar to the magnetic field. So if a magnetic field can lead to a current like this, then a rotation would also lead to a current. That's at the very qualitative level. Though in order to fix this relative coefficient, one need to go a little bit deeper into this analogy. Okay, there is not many. Yeah.
I have one question. So how can we explain the t-squared term with the chirovoltical effect?
Yeah, that t-squared term is this still a mystery, at least to me. It jumped out from. It's actually consistent. We can check that the entropy from this entropy production analysis, this t-squared term is allowed. It's allowed by requiring the S over dt greater than 0. It's allowed with a coefficient that has to be fixed. That is, this coefficient cannot depend on anything, cannot depend on temperature or chemical potential. It has to be a number. It has to be a number. And that number is it turned out that this number, and some people have proposed a way to answer this question, but this number turned out to be related to another anomalies. That is the so let me draw a diagram. This is the axial current, and then this is graviton. And let me write down this equation that time. Right, this very roughly R time R dual. I'm not going to put the indices. Basically, it says that if I have a curved background, that curved background can also create chiral particles. And that seems to be that seems to have some deep reason, which I myself haven't been able to understand. But there are articles in the literature, one by Komarbotsky, where he provides an explanation why that coefficient of a very physical, basically it's a very physical coefficient. It's when you rotate a system, what is the strength of this chirovoltical effect as a function of temperature, how this can be related to something quite abstract, that is the the anomalies that involve the gravitational field. Yeah, I hope that partially answered your question.
Thank you.
There are not many experimental verification of this effect. There are some hints in heavy ion collision, but I'm going to tell you about an experiment in Dirac and Weill semimeter. So here in this system, we have an even number of these Dirac nodes. Some material may have up to like 24 of this Dirac point. So this number of Dirac points has to be even. Is the left-handed and right-handed Dirac point. So in this experiment, what they do is that they put a system in the magnetic field. Let's put a system in a magnetic field B, and then turn on an electric field E, and measure what is measured. What one measure is the conductivity as a function of the magnetic field. So basically, one try to determine the dependence of the conductivity on the magnetic field. So these anomalies influence the effect, the thing in the following way. So let's imagine that we have these two Dirac points. We know that the right-handed fermion is produced by E dot B, and left-handed is destroyed by E dot B. So that means that particle will move from the left point to the right. It's moved somewhere under the Dirac C. Then the Dirac, the level, if the Fermi level in the beginning is like that, at some point it will be imbalanced, or be like that. Basically, the difference between the number right minus number left is constantly increasing with time. So in the real material, that process, if nothing prevents that process from stopping, it will continue forever. But in the real material, there are processes of relaxation where particle due to collision with impurities, etc., would flip its chirality. That is, it moves from the vicinity of one Dirac point to the vicinity of another Dirac point. So basically, there is some relaxation that counteracts the appearance of the imbalance. So the imbalance would be pumped by E dot B, but is relaxed back to zero by the relaxation. So there's some relaxation time. Yeah. To wait long enough, this process reaches some kind of a stationary state where the pumping is completely balanced by the relaxation. So that then it means that n right minus n left equal E dot B times tau, the relaxation time. Okay, so once that is established, there is a difference in the chemical potential of the right and the left. Right-handed fermion would have slightly higher chemical potential than the left-handed fermion. And the difference is proportional to the difference in the density. And again, it's proportional to E dot B times tau. So that is one, the first, this is the first effect of anomalies. The second effect of anomalies on top of that is that chemical potential in a, so there is a chiral magnetic effect, that is if we have a magnetic field and chemical potential, we generate current. So this current, that is the current of right-handed fermion plus current of left-handed fermions, right? And that's mu right B. There is a term that's proportional to mu right B plus mu left B, but minus mu left B, because the sign of the anomalies of the right and the left-handed fermions are different. So that is the chiral magnetic effect. And that is now equal to mu right minus mu left. That is E dot B times B times tau. So the anomalies give rise to contribution proportional to B squared. So if E and B is point to the same direction, I have A times B squared times tau. So it's sigma then equal to some sigma 0 plus something proportional to B squared times tau. That's a prediction of a very simple hydrodynamic model of this process. So it would work very well if tau for some reason is large. If tau, the relaxation time is large, then this effect becomes very big. This becomes very big. Magnetic field leads to typically also there's other ways that the magnetic field changes conductivity of the material. Just because particles start to move in orbit and their collisions are different, leads to a change of the conductivity with respect to magnetic field. But if tau is large, then this effect is dominant. But for some unknown reason, the experiment in most of this material, despite and Dirac semi-metal, when they measure the conductivity, they see so very roughly. They see something like the conductivity goes up, as if this is very consistent with this formula, and then at some point this formula breaks down and go down. The conductivity becomes smaller as a function of chemical of B. So if you are an optimist, you would look at this region and claim that we have seen the effect of anomalies in this material. And using this formula here, one can estimate the relaxation time, and in fact that relaxation time is somewhat larger than the rate of other processes at equilibrium. And so that seems to be consistent with the experiment. The reason for that part of the curve is still not very clear. At larger magnetic field, it starts to go down. And also one thing that seems to be also unclear is the angular dependence. On the angle between E and B. So this formula that I have derived here requires that E and B point in the same direction. If they point in slightly different direction, we expect some cosine, some power of the cosine of the angle. The experimental result showed a very sensitive dependence on the angle, much more sensitive than, for example, cosine theta square, or that would appear from this, that arises from this simple treatment. So that is still one thing that I don't completely understand how to explain that. Okay.